This presentation is delivered by the Stanford Center for Professional Development.
What I want to do today is continue our discussion of naive Bayes, which is the learning algorithm that I just started to discuss in the previous lecture, and talk about a couple of different event models in naive Bayes. And then I'll take a brief digression to talk about neural network, which is something that I actually won't spend a lot of time on. And then I want to start to talk about support vector machines. And support vector machines is the learning algorithm, is the supervised learning algorithm that many people consider the most effective off-the-shelf supervised learning algorithm. That point of view is debatable, but there are many people that hold that point of view. And we'll start discussing that today. And this will actually take us a few lectures to complete. So let's talk about naive Bayes. To recap from the previous lecture, I started off describing spam classification as the motivating example for naive Bayes, in which we would create feature vectors like these, right, that correspond to words in a dictionary. And so, based on what words appear in a piece of email, we're represented as a feature vector with ones and zeros in the corresponding places. And naive Bayes was a generative learning algorithm. And by that I mean is an algorithm in which we model P of x given y. And for naive Bayes specifically, we modeled it as product from I equals 1 to n, P of xi given y. And also we modeled P of y. And then we use Bayes' rule, right, to combine these two together. And so our predictions, when you're given a new piece of email, you want to tell if it's spam or not spam, you predict argmax over y, P of y given x, which by Bayes' rule is argmax over y, P of x given y, times P of y. Okay? So this is naive Bayes. And just to draw attention to two things. One is that in this model, each of our features were 0, 1, so indicating where the different words appear. And the length of the feature vector was, so the length n of the feature vector was, the number of words in the dictionary. So it might be, for instance, on the order of 50,000 words, say. What I want to do now is describe two variations on this algorithm. The first one is the simpler one, which is just a generalization to if xi takes on more values. So, one of the things that's commonly done is to apply naive Bayes to problems where some of these features xi takes on k values rather than just 2 values. And in that case, you actually build a very similar model where P of x given y is really the same thing, right? Where now these are going to be multinomial probabilities rather than Bernoulli's, because the xi's can maybe take on up to k values. It turns out one situation where this arises very commonly is if you have a feature that's actually continuous valued and you choose to discretize it. You choose to take a continuous value feature and discretize it into a finite set of k values. And so as a concrete example, if you remember our very first supervised learning problem of predicting the price of houses. If you have a classification problem on these houses, so based on features of a house, if you want to predict whether or not the house will be sold in the next 6 months, say, that's a classification problem. If you want to use naive Bayes, then given a continuous value feature, like the living area, one pretty common thing to do would be to take the continuous value living area and just discretize it into a few discrete buckets. And so depending on whether the living area of the house is less than 500 square feet or between 1,000 and 1,500 square feet, and so on, or whether it's greater than 2,000 square feet, you choose the value of the corresponding feature xi to be 1, 2, 3, or 4. Okay? So that was the first variation or generalization of naive Bayes I want to talk about. I should check. Are there questions about this? Okay, cool. And so it turns out in practice, it's fairly common to use about 10 buckets to discretize a continuous value feature. I drew 4 here only to save on writing. The second, and so final variation I want to talk about for naive Bayes is a variation that's specific to classifying text documents, or more generally for classifying sequences. So a text document, like a piece of email, you can think of as a sequence of words. And you can apply this sort of model I'm about to describe to classifying other sequences as well. But let me just focus on text. And here's the idea. So the naive Bayes algorithm, as I've described it so far, right? Given a piece of email, we were representing it using this binary vector value representation. And one of the things that this loses, for instance, is the number of times that different words appear. Right? So for example, if some word appears a lot of times, if you see the word, buy a lot of times, if you see the word, I don't know, Viagra seems to be a common email example. If you see the word Viagra a ton of times in email, it's more likely to be spammed than if it appears, I guess, only once. Even once, I guess, is enough. So let me describe a different, what's called an event model for naive Bayes that would take into account the number of times a word appears in an email. And to give this previous model a name as well, this particular model for text classification is called the multivariate Bernoulli event model. It's not a great name. Don't worry about what the name means. It refers to the fact that there are multiple Bernoulli random variables, but it's really don't worry about what the name means. In contrast, what I want to do now is describe a different representation for email in terms of the feature vector, and this is called the multinomial event model. And again, there is a rationale behind the name, but it's slightly cryptic, so don't worry about why it's called the multinomial event model. It's just called that. And here's what we're going to do. Given a piece of email, I'm going to represent my email as a feature vector. And so my ith training example, xi, will be a feature vector xi subscript 1, xi subscript 2, comma, xi subscript ni, where ni is equal to the number of words in this email, right? So if one of my training examples is an email with 300 words in it, then I represent this email via feature vector with 300 elements. And each of these elements of the feature vector, let me just write this as x subscript j, these will be an index into my dictionary. Okay, and so if my dictionary has 50,000 words, then each position in my feature vector will be a variable that takes on one of 50,000 possible values corresponding to corresponding to what word appeared in the jth position of my email. Okay, so in other words, I'm going to take all the words in my email and create a feature vector that just says which word in my dictionary was each word in the email. Okay, so a different definition of ni now. Ni now varies and is different for every training example, and these xj's now indexed into the dictionary. These the components of the feature vector are no longer binary random variables. They're these indices in the dictionary and take on a much larger set of values. And so our generative model for this will be that the joint distribution over x and y will be that, where again n is now the length of the email. Right? So the way to think about this formula is you imagine that there was some probability distribution over emails. There's some random distribution that generated emails, and that process proceeds as follows. First, y is chosen. First, the class label is someone going to send you spam email or not spam email is chosen first. Right? And so first y, the random variable y, the class label, spam or not spam, is generated. And then, having decided whether to send you spam or not spam, someone iterates over, all 300 positions of the email, right? All 300 words that they're going to compose in this email, and will generate words from some distribution that depends on whether they chose to send you spam or not spam. So if they send you spam, they'll send you words. They'll tend to generate words like, buy and Viagra and whatever, discount, sale, whatever. And if someone chose to send you not spam, then they'll send you the more normal words you get in the email. Okay. So just careful, right? Xi here has a very different definition from the previous event model, and n has very different definition from the previous event model. And so the parameters of this model are, let's see, phi subscript k given y equals 1, which is the probability that, conditioned on someone deciding to send you spam, what's the probability that the next word they choose to email you in their spam email is going to be word k. And similarly, so same thing. Well, I'll just write it out, I guess. And phi y, which is the same as before. Okay, so these are the parameters of the model. And given a training set, you can work out the maximum likelihood estimates of the parameters. So the maximum likelihood estimate of the parameters will be equal to, and now I'm going to write one of these, big indicator function things again. It'll be a sum over your training set. Indicator, whether that was spam times sum over all the words in that email, where n subscript I is the number of words in email I in your training set, times indicator xij sk times ai. Okay, so the numerator says sum over all your emails and take into account all the emails that had class label 1, take into account only all the emails that were spam. If y equals 0, then this is 0 and this will go away. And then times sum over all the words in your spam email and count up the number of times you observed word k in your spam emails. So in other words, the numerator is look at all the spam emails in your training set and count up the total number of times the word k appeared in this email. The denominator then is sum over our entire training set of whenever one of your examples of spam, sum up the length of that spam email. And so the denominator is the total length of all the spam emails in your training set. And so the ratio is just out of all your spam emails, what is the fraction of words in all your spam emails that were word k. And that's the estimate for the probability of the next piece of spam mail generating the word k in any given position. Okay. And at the end of the previous lecture, I talked about Laplace moving. And so when you do that as well, you add 1 to the numerator and k to the denominator. And this is the Laplace smoothed estimate of this parameter. Okay, and similarly, you do the same thing for, and you can work out the estimates for the other parameters yourself. Okay, so it's very similar. Yeah.
I'm sorry, on the right board, on the top, I was just wondering what the x sub I is and what the n is.
Right. Okay. So in this second event model, the definition for xi and definition for n are different, right? So here, well, this is for one example, xy. So here, n is the number of words in a given email, right? And if it's the I email, it's subscripting thing, this n subscript I. And so n will be different for different training examples. And here, xi will be, these values from 1 to 50,000. And xi is essentially the identity of the I word in a given piece of email. Okay, so that's why this is looping, or this is a product over all the different words of your email of the probability of the I word in your email, conditional on y. Yeah. Actually, you know what? I apologize. I just realized I overloaded notation. Right. Maybe I shouldn't have used k here. Let me use a different alphabet and see if that makes sense. Does that make sense? Oh, you know what? I'm sorry. You're absolutely right. Thank you. Right. So this in Laplace moving, that shouldn't be k. This should be 50,000. If you have 50,000 words in your dictionary. Yeah, thanks. Right. I stole notation from the previous lecture and then translate it appropriately. So Laplace moving, right. This is the number of possible values that the random variable xi can take on. Cool. Just raise your hand if this makes sense. Yeah, okay. Cool. Some of you. Are there more questions about this?
For Laplace moving, the denominator, the plus k, is the number of values that y could take.
Yeah, and let's see. So Laplace moving is a method to give you sort of hopefully better estimates of the probability distribution over a multinomial. And so, was I using x or y in the previous lecture? So if you're trying to estimate the probability over a multinomial, I think x and y are different. I think, was it x or y? I think it was x actually. Well, oh, I see. Right. I think I was using a different definition for the random variable y. But when suppose you have a multinomial random variable, x, which takes on let's use a different alphabet. Suppose you have a multinomial random variable x, which takes on L different values. Then the maximum likelihood estimate for for the probability of x, p of x equals k, will be equal to the number of observations the maximum likelihood estimate for the probability of x being equal to k will be the number of observations of x equals k divided by the total number of observations of x. Okay, so that's the maximum likelihood estimate. And to add Laplace moving to this, you sort of add 1 to the numerator and you add L to the denominator, where L is the number of possible values that x can take on. So in this case, this is a probability that x equals k, and x can take on 50,000 values. If 50,000 is the length of your dictionary, it may be something else, but that's why I add 50,000 as a denominator. What other questions? Yeah.
Is there a specific definition for a maximum likelihood estimation of a parameter? We've talked about it a couple times, and all the examples make sense, but I don't know what the general formula for it is.
I see. Yeah, right. So the definition for maximum likelihood. So the question is, what's the definition for maximum likelihood estimate? so actually, in today's lecture and the previous lecture, when I talked about Gaussian discriminant analysis, I was sort of throwing out the maximum likelihood estimates on the board without proving them. The way to actually work this out is to actually write down the likelihood. Actually, well. So the way to figure out all of these maximum likelihood estimates is to write down the likelihood of the parameters. Phi k given y equals 0, phi y, right? And so given a training set, the likelihood, I guess I'm actually writing the log likelihood, will be the log of the product of I equals 1 to m, p of xi comma yi, parameterized by these things. Okay. Where p of xi comma yi, right, this is given by ni with xij given yi, parameterized by, well, I'll just drop the parameters to write this more simply. I'll just put it in. Times p of yi. Okay, so this is my log likelihood, and so the way you get the maximum likelihood estimate of the parameters is sort of given a fixed training set, given a set of xi, yi's, you maximize this in terms of these parameters, and then you get the maximum likelihood estimates that I've been writing out. So in the previous lecture and today's lecture, I wrote out some maximum likelihood estimates for the Gaussian discriminant analysis model and for naive Bayes, and then I sort of didn't prove them. But you get to sort of play with that yourself in the homework problem as well. And so for one of these models, and you'll be able to verify that when you maximize the likelihood and maximize the log likelihood, that hopefully you do get the same formulas as well as throwing up on the board. But the way it's defined, the way these are derived is by maximizing this. Okay. Cool. All right. So that wraps up what I want to say about so that more or less wraps up what I want to say about naive Bayes. And it turns out that for text classification, the naive Bayes algorithm with the second event model, the loss of naive Bayes model I presented with the multinomial event model, it turns out that almost always does better than the first naive Bayes model I talked about when you're applying it to the specific case, to the specific of text classification. And one of the reasons that's hypothesized for this is that the second model, the multinomial event model, takes into account the number of times a word appears in a document, whereas the formal model doesn't. I said in truth, that it actually turns out not to be completely understood why the latter model does better than the former one for text classification. And so researchers are still debating about it a bit. But if you ever have a text classification problem, naive Bayes classifier is probably not by far the best learning algorithm out there, but is relatively straightforward to implement and is a very good first algorithm to try if you have a text classification problem. Okay, that's a good question. Yeah.
So the second model is still position invariant, right? It doesn't actually care whether words are relative to each other.
Yep.
And I mean, I assume that like markup model where you do have that information, and does that usually do better if you have enough data?
Yeah. So the question is the second model, right? Second model, the multinomial event model, actually doesn't care about the ordering of words. You can shuffle all the words in the email, and it does exactly the same thing. So in natural language processing, this model actually has another name. It's called the unigram model in natural language processing. And there's some other models like so say higher order Markov models that take into account some of the ordering of the words. It turns out that for text classification, the models like the bigram models, the trigram models, I believe they do only very slightly better, if at all. But that's when you're applying them to text classification. Okay. All right. So the next thing I want to talk about is to start to get into discussion of nonlinear classifiers. So it turns out, well, and so the very first classification algorithm we talked about was logistic regression, which had the following form for hypothesis. And you can think of this as predicting 1 when this estimated probability is greater than or equal to 0.5, and predicting 0, right, when the when this is less than 0.5. And given a training set, right, logistic regression will maybe do gradient descent or something, or use Newton's method to find a straight line that reasonably separates the positive and negative classes. But sometimes the data set just can't be separated by a straight line. So is there an algorithm that will let you start to learn these sorts of nonlinear decision boundaries? And so how do you go about getting a nonlinear classifier? And by the way, one cool result is that, remember I said, when we talked about generative learning algorithms, I said that, if you assume y given x is exponential family, right, with parameter eta, and if you build a generative learning algorithm using this, right, equals 1, if this is eta 1, this is exponential family, with natural parameter eta 0, right? I think when we talked about Gaussian discriminant analysis, I said that if this holds true, then you end up with a logistic posterior. It actually turns out that the naive Bayes model actually falls into this as well. So the naive Bayes model actually falls into this exponential family as well. And therefore, under the naive Bayes model, you're actually using this sort of linear classifier as well. Okay. So the question is, how can we start to get nonlinear classifiers? And I'm going to talk about one method today, which is let me just want to talk about it very briefly, which is taking a simpler algorithm like logistic regression and using it to build up to more complex nonlinear classifiers. Okay. So to motivate this discussion, I'm going to use a little picture. Let's see. So suppose you have features x1, x2, and x3. And so by convention, I'm going to follow our early convention that x0 is set to 1. And so I'm going to use a little diagram like this to denote a logistic regression unit. Okay? So think of a little picture like this, this little circle as denoting a computation node that takes as input, several features, and then it outputs another number that's x subscript theta of x, given by a sigmoid function. And so this little computational unit will have parameters theta. Now, in order to get nonlinear decision boundaries, all we need to do, or at least one thing we could do, is just come up with a way to represent hypotheses that can output nonlinear decision boundaries, right? And so this is, when you put a bunch of those little pictures that I drew on the previous board, you can then get what's called a neural network, in which, think of having my features here, and then I would feed them to, say, a few of these little sigmoidal units. And these together will feed into yet another sigmoidal unit, say, which will output my final output h subscript theta of x. Okay? And just to give these things names, let me call the values output by these three intermediate sigmoidal units, and we call them A1, A2, A3. And let me just be completely concrete about what this formula represents, right? So each of these units in the middle will have their own associated set of parameters. And so the value A1 will be computed as G of X transpose, and then some set of parameters which are write as theta 1. And similarly, A2 will be computed as G of X transpose theta 2, and A3 will be G of X transpose theta 3, where G is the sigmoid function, right? So G of Z. And then finally, our hypothesis will output, G of A transpose theta 4, right? Where, this A vector is a vector of A1, A2, A3. You can append another 1 to it at first if you want. Okay? Let me just draw up here. Yes. Sorry about the cluttered board. And so H subscript theta of X, this is a function of all the parameters theta 1 through theta 4. And so one way to learn parameters for this model is to write down the cost function, say J of theta equals 1/2 sum from I equals 1 to m yi minus H subscript theta of xi squared, say. So that's our familiar quadratic cost function. And so one way to learn the parameters of an algorithm like this is to just use gradient descent to minimize J of theta as a function of theta. Okay, so you can apply gradient descent to minimize this squared error, which stated differently means you use gradient descent to make the predictions of your neural network as close as possible to what you observed as the labels in your training set. Okay? So it turns out gradient descent on this sort of neural network is a specific name. The algorithm that implements gradient descent is called backpropagation. So if you ever hear that, all that means is it just means gradient descent on a cost function like this or a variation of this on a neural network that looks like that. Well, this algorithm actually has some advantages and disadvantages, but let me actually show you. So let's see. One of the interesting things about the neural network is that you can look at what these intermediate nodes are computing, right? So this is this neural network has sort of what's called a hidden layer before you then have the output layer, and more generally, you can actually have inputs feed into these computation units, feed into more layers of computation units, to even more layers, to more layers, and then finally you have an output layer at the end. And one cool thing you can do is look at all of these intermediate units. Look at these units in what's called a hidden layer of the neural network. Don't worry about why it's called that. Look at computations, the hidden units, and ask, what is the hidden unit computing in the neural network? So to maybe get a better sense of what neural networks might be doing, let me show you a video, and switch to the laptop, of, it's made by a friend, Jan LeCun, who's currently a professor at New York University. Can I show a video on the laptop? So let me show you a video from Jan LeCun on a neural network that he developed for Hamilton digit recognition. There was one other thing he did in this neural network that I'm not going to talk about, called a convolutional neural network. But well, his system is called LeNet, and let's see, should you put on the laptop display? Actually, maybe or you can just put on the screens at the side, that will work too, if the big screen isn't working. let's see. I'm just trying to think, okay, how do I keep you guys entertained while we're waiting for the video to come on? Well, let me say a few more things about neural networks. So it turns out that when you write out a quadratic cost function, like I wrote down on the chalkboard just now, it turns out that unlike logistic regression, that will almost always correspond to a non-convex optimization problem. And so, whereas for logistic regression, if you run gradient descent or Newton's method or whatever, you converge the global optima. This is not true for neural networks. In general, there are lots of local optima, and it's sort of a much harder optimization problem. So neural networks, if you're sort of familiar with them and you're good at making design choices, like what learning rate to use and how many hidden units to use and so on, you can sort of get them to be fairly effective. And there's sort of often ongoing debates about, is this learning algorithm better or is that learning algorithm better? The vast majority of machine learning researchers today seem to perceive support vector machines, which is what I'll talk about later, to be a much more effective off-the-shelf learning algorithm than neural networks. This point of view is contested a bit. So neural networks are not something that I personally use a lot right now because it's a hard optimization problem. It usually takes a while to converge. But it actually sort of works. It sort of works reasonably well. But it's just because it's fairly complicated. It's not an algorithm that I use commonly or that my friends use all the time. Oh, cool. So, but let me actually go ahead and show you an example of a neural network, which was for many years, the most effective learning algorithm before support vector machines were invented. So here's Jan Kun's video, and well, there's actually audio on this too. That's not important. But so let me tell you what's happening. This is what you're seeing is a trained neural network, and this display where my mouse pointer is pointing, right? This big 3 there is the input to the neural network. So you're showing the neural network this image, and it's trying to recognize what is this. The final answer output by the neural network is this number up here, right below where it says LearnNet 5. And the neural network correctly recognizes this image as a 3. And if you look to the left of this image, what's interesting about this is the display on the left portion of this is actually showing the intermediate computations to the neural network. In other words, it's showing you what are the hidden layers of the neural network computing. And so, for example, if you look at this one, the third image down from the top, this seems to be computing, certain edges in the digits, right? Whereas computing digits on the right-hand side of the bottom or something of the input display of the input image. Okay, so let me just play this video, and you can see some of the inputs and outputs of the neural networks, and so very different fonts. Robustness to noise. Multiple digits. That's kind of cool. All right. So, just for fun, let me show you one more video, which was, let's see, this is another video from the video series, The Machine That Changed the World, which was produced by WGBH Television in cooperation with British Broadcasting Corporation, and it was aired on PBS a few years ago, I think. I'm going to show you a video describing the NetTalk neural network, which was developed by Terry Sonowski, who's a researcher. So NetTalk was actually one of the major milestones in the history of neural networks. And the specific application is getting a neural network to read text. So in other words, can you show, piece of English to a computer and have a computer read, so verbally produce sounds that correspond to reading out the text. And it turned out in the history of AI and the history of machine learning, this video creates a lot of excitement about neural networks and about machine learning. Part of the reason was that Terry Sonowski, had the foresight to choose to use in his video a childlike voice talking about visiting your grandmother's house and so on. You see it in a second. And so this really created the impression of the neural network being like a young child learning how to speak and talking about going to their grandmothers and so on. So this actually helped generate a lot of excitement within academia and outside academia on neural networks, sort of early in the history of neural networks. Let me just go ahead and show you the video.
You're going to hear first what the network sounds like at the very beginning of the training. And it won't sound like words, but it'll sound like attempts that will get better and better with time.
The
network takes the letters, say the phrase grandmother's house, and makes a random attempt at pronouncing it.
Grandmother's house.
The phonetic difference between the guess and the right pronunciation is sent back through the network.
Grandmother's house.
By adjusting the connection strengths after each attempt, the net slowly improves.
And finally, after letting it train overnight, the next morning, it sounds like this.
Grandmother's house. I like to go to my grandmother's house. Well, because she gives us candy. Well,
NetTalk understands nothing about the language. It is simply associating letters with sounds.
All right. So at the time this was done, this is I think this is an amazing piece of work. I should say, today there are other text-to-speech systems that work better than what you just saw. And I guess you also appreciate this, getting candy from your grandmother's house. This would have been less impressive. We're talking about the Dow Jones falling 15 points and profit taking, whatever. Right? So, but I want to show that just because that was another cool major landmark in the history of neural networks. Okay, so let's switch back to the chalkboard. What I want to do next, what I want to do next is tell you about support vector machines. Okay, that sort of wraps up our discussion on neural networks. So I started off talking about neural networks by motivating it as a way to get us to output nonlinear classifiers. Right? I didn't really prove it, but it turns out that you'd be able to come up with nonlinear decision boundaries using a neural network like what I drew on the chalkboard earlier. Support vector machines will be another learning algorithm that will give us a way to come up with nonlinear classifiers. There's a very effective off-the-shelf learning algorithm. But it turns out that in the discussion in the progression or development I'm going to pursue, I'm actually going to start off by describing yet another class of linear classifiers with linear decision boundaries, and only be later, sort of in the next lecture or the one after that, that will then take the support vector machines idea and sort of do some clever things to it to make it work very well to generate nonlinear decision boundaries as well. Okay, but we'll actually start by talking about linear classifiers a little bit more. And to do that, I want to convey two intuitions about classification. One is, you think about logistic regression, right? We had this logistic function that was outputting the probability that y equals 1. And it crosses this line at 0. So when you run logistic regression, I want you to think of it as an algorithm that computes theta transpose x, and then it predicts 1, right? If and only if theta transpose x is greater than 0, right? IFF stands for if and only if, right? It means the same thing as a double implication. And it predicts 0 if and only if theta transpose x is less than 0, say. Okay? So if it's the case that theta transpose x is much greater than 0, the double greater than sign means it's a much greater than, right? So if theta transpose x is much greater than 0, then think of that as a very confident prediction that y is equal to 1, right? If theta transpose x is much greater than 0, then we're going to predict 1, and moreover, we're very confident it's 1. And the picture for that is, if theta transpose x is way out here, then we're estimating that the probability of y being equal to 1 on the sigmoid function will be very close to 1. And in the same way, if theta transpose x is much less than 0, then we're very confident that y is equal to 0. So, won't it be nice? So when we fit logistic regression or some other classifier to a training set, then won't it be nice if, right, for all I such that y is equal to 1, we have theta transpose xi is much greater than 0, and for all I such that y is equal to 0, we have theta transpose xi is much less than 0. Okay, so won't it be nice if this is true? That for all that essentially, if for our training set we can find parameters theta, so that our learning algorithm not only makes correct classifications on all the examples in the training set, but further, it is very confident about all of its correct classifications. So this is the first intuition that I want you to have, and we'll come back to this first intuition in a second when we talk about functional margins. Okay, we'll define this later. The second intuition that I want to convey it turns out for the rest of today's lecture, I'm going to assume that the training set is linearly separable. Okay, so by that I mean for the rest of today's lecture, I'm going to assume that there is indeed a straight line that can separate your training set, and we'll remove this assumption later. But just to develop the algorithm, let's say we have a linearly separable training set. And so there's a sense that out of all the straight lines that separate the training set, maybe that straight line isn't such a good one. And that one actually isn't such a great one either. But maybe that line in the middle is a much better linear separator than the others. And one reason that when you and I look at it, this one seems best is because this line is just further from the data. Right? That it separates the data with a greater distance between your positive and negative examples and the decision boundary. Okay? And this second intuition we'll come back to shortly about this line, this final line that I drew being maybe the best line. This notion of distance from the training examples, this is the second intuition I want to convey. And we'll formalize it later when we talk about geometric margins of a classifiers. Okay? So, so in order to describe the support vector machine, unfortunately I'm going to have to pull a notation change. And unfortunately, it sort of wasn't possible to do logistic regression and support vector machines, and all the other algorithms using one completely consistent notation. And so I'm actually going to change the notation slightly for linear classifiers, and that'll actually make it much easier for us to, that'll make it much easier later today and in next week's lectures to actually talk about support vector machine. But the notation that I'm going to use for the rest of today and for most of next week will be that my labels y, instead of being 0, 1, they'll be -1 and +1. And right. In the development of a support vector machine, we will have a hypothesis, output values that are either +1 or -1. And so, we'll let g of z be equal to 1 if z is greater than or equal to 0 and -1 otherwise, right? So just rather than 0 and 1, we change everything to +1 and -1. And finally, whereas previously I wrote, right, g subscript theta of x equals g of theta transpose x, and we had the convention that x0 is equal to 1, right? And so x is an Rn plus 1. I'm going to drop this convention of letting x0 equals to 1 and letting x be an Rn plus 1. And instead, I'm going to parameterize my linear classifier as h subscript w comma b of x equals g of w transpose x plus b. Okay? And so, b just now plays the role of theta 0, and w now plays the role of the rest of the parameters, theta 1 through theta n. Okay? So just this, by separating out the intercept term b rather than lumping it together, it will make it easier for us to develop support vector machines. So, yes? Yes, right, yes. So w is, right, so w is a vector in Rn, and x is now a vector in Rn rather than n plus 1. And lowercase b is a real number. Okay. Now let's formalize the notion of functional margin and geometric margin. Let me make a definition. I'm going to say that the functional margin of a hyperplane WB with respect to a specific training example, xi, yi, is, WRT stands for with respect to. The functional margin of a hyperplane WB with respect to a certain training example, xi, yi, is going to define as gamma hat I equals yi times W transpose xi plus b. Okay? And so a set of parameters W comma b defines a classifier, or it sort of defines a linear separating boundary. And so when I say hyperplane, I just mean the decision boundary that's defined by the parameters W comma b. you know what, if you're confused by the hyperplane term, just ignore it. The hyperplane of a classifier with parameters WB with respect to a training example is given by this formula. Okay? And the interpretation of this is that, you know, if yi is equal to 1, then for you to have a large functional margin, we want W transpose xi plus b to be large, right? And if yi is equal to -1, then in order for the functional margin to be large, we sort of want the functional margin to be large. But in order for the functional margin to be large, if yi is equal to -1, then the only way for this to be big is if W transpose xi plus b is much less than 0. Okay? So this captures the intuition that we had earlier about functional margins, that if the intuition we had earlier that if yi is equal to 1, we want this to be big, and if y is equal to -1, we want this to be small, and this sort of captures the two cases into one statement that we'd like the functional margin to be large. And notice also that so long as yi times W transpose xi plus b, so long as this is greater than 0, that means we classified it correctly. Okay. And one more definition, I'm going to say that the functional margin of a hyperplane with respect to an entire training set is going to be going to define gamma hat to be equal to min over all your training examples of gamma hat I. Right. So if you have a training set, if you have just more than one training example, I'm going to define the functional margin with respect to the entire training set as, you know, the worst case of all of your functional margins of the entire training set. And so for now, we should think of the first functional margin intuition as saying that we would like the functional margin to be large. And for our purposes for now, let's just say we would like the worst case functional margin to be large. Okay? And we'll change this a little bit later as well. Now, turns out that there's one little problem with this intuition that makes it, that will sort of add just later, which is that it actually turns out to be very easy to make the functional margin large. Right? So for example, suppose I have a classifier with parameters w and b. If I take w and multiply it by 2, and take b and multiply it by 2, then if you refer to the definition of a functional margin, I guess that was what? Gamma hat I equals yi times W transpose x plus b, right? If I double w and b, then I can easily double my functional margin. So this goal of making the functional margin large, you know, in and of itself isn't so useful because you easily make the functional margin arbitrarily large just by scaling up the parameters. And so maybe one thing we need to do later is add a normalization condition. For example, maybe we want to add a normalization condition that the norm, the L2 norm of the parameter w is equal to 1. We'll come back to this in a second. Oh, right, and so, yeah. Okay. Now let's talk about, let's see how much time I have, 15 minutes. Well, so I'm trying to decide how much to try to do in the last 15 minutes. Okay, so let's talk about the geometric margin. And so the geometric margin of a training example, it's convenient, let me just reuse this one. Well, right? So the decision boundary of my classifier is going to be given by the plane W transpose x plus b is equal to 0. Okay, right? And these are the x1, x2 axes, say. And I'm going to draw relatively few training examples here. Let's say I'm drawing deliberately few training examples so that I can add things to this. Okay, and so assuming we classified an example correctly, I'm going to define the geometric margin as just a distance, so just a geometric distance between a point between the training example, between the training example xi, comma yi, and the distance given by this separating line, given by this separating hyperplane. Okay, that's what I'm going to define the geometric margin to be. And so I'm going to do some algebra fairly quickly in case it doesn't make sense and read through the lecture notes more carefully for details. So by standard geometry, the normal, or in other words, the vector that's at 90 degrees to the separating hyperplane is going to be given by w divided by the norm of w. That's just how planes in high dimensions work. And if this looks somewhat mysterious to you, so take a look at the lecture notes on the website. And so let's say this distance is gamma I, okay? And so I'm going to use the convention that I'll put a hat on top when referring to functional margins and no hat on top for geometric margins. So let's say geometric margin of this example is gamma I. That means that this point here, right, is going to be xi minus gamma I times w over norm of w. Okay? Because w over norm of w is a unit vector, is a length 1 vector that's normal to the separating hyperplane. And so when we subtract gamma I times the unit vector from this point xi, right? This point here is xi. So xi minus, this little vector here is going to be this point that I've drawn as a heavy circle. Okay, so this heavy point here is xi minus this vector, and this vector is gamma I times w over norm of w. Okay? And so, because this heavy point is on the separating hyperplane, right, this point must satisfy w transpose times that point equals 0, right? Because all points x on the separating hyperplane satisfy the equation w transpose x plus b equals 0. And so this point is on the separating hyperplane, therefore it must satisfy w transpose this point. Oh, excuse me. Plus b is equal to 0. Okay? Raise your hand if this makes sense so far. Oh, okay, cool, most of you. But again, I'm sort of being slightly fast and loose with the geometry. So if you're not quite sure why there's a normal vector or how I subtracted this or whatever, then take a look at the details in the lecture notes. And so what I'm going to do is I'll just take this equation and I'll solve for gamma, right? So this equation I just wrote down, solve this equation for gamma I, and you find that you solve that previous equation for gamma I, well, I'll just do it. You have w transpose xi plus b equals gamma I times w transpose w over norm of w. That's just equal to gamma times the norm of w, because w transpose w is the norm of W squared. And therefore, gamma is just transpose x plus b. Okay? And in other words, this little calculation just showed us that if you have a training example, xi, then the distance between xi and the separating hyperplane defined by the parameters w and b can be computed via this formula. Okay? So the last thing I want to do is actually take into account the sign of the correct classification of the training example. So I've been assuming that, you know, we've been classifying an example correctly. So more generally, define the geometric margin of a training example to be gamma I equals yi times that thing on top. Okay? And so this is very similar to the functional margin, except for the normalization by the norm of W. And so as before, you know, this says that so long as we would like the geometric margin to be large. And all that means is that so long as we're classifying the example correctly, we would ideally hope for the example to be as far as possible from the separating hyperplane, so long as it's on the right side of the separating hyperplane. And that's what yi multiplied into this does. And so a couple of easy facts. One is if the norm of W is equal to 1, then the functional margin is equal to the geometric margin. You can see that quite easily. And more generally, the geometric margin is just equal to the functional margin divided by the norm of W. Okay? Let's see. Okay. And so one final definition is so far I've defined the geometric margin with respect to a single training example. And so as before, I'll define the geometric margin with respect to an entire training set as gamma equals min over I of gamma I. All right? And so the maximum margin classifier, which is a precursor to the support vector machine, is the learning algorithm that chooses the parameters W and B so as to maximize the geometric margin. And so I'll just write that down. The maximum margin classifier poses the following optimization problem. It says, choose gamma, W, and B so as to maximize the geometric margin. Subject to that, yi times, well, this is just one way to write it. Subject to, actually, did I write it like that? Yeah, fine. There are several ways to write this, and one of the things we'll do next time is actually try to figure out if I can do this in 5 minutes. I'm guessing this could be difficult. Yeah. Well, so this maximum margin classifier is a maximization problem over parameter gamma, W, and B. And for now, it turns out that the geometric margin doesn't change depending on the norm of W, right? Because in the definition of the geometric margin, notice that we're dividing by the norm of W anyway. So you can actually set the norm of W to be anything you want. You can multiply W and B by any constant. It doesn't change the geometric margin. This will actually be important. We'll come back to this later. Right? Notice that you can take the parameters WB and you can impose any normalization constant to it. Or you can change W and B by any scaling factor. You replace them by 10W and 10B, whatever. And it does not change the geometric margin. Okay? And so in this first formulation, I'm just going to impose a constraint, say that the norm of W must be equal to 1. And so the function of the geometric margins will be the same. And then we'll say maximize the geometric margin subject to, you maximize gamma subject to that every training example must have geometric margin, at least gamma. And this is the geometric margin because when the norm of W is equal to 1, then the function of the geometric margin are identical. Okay? So this is a maximum margin classifier, and it turns out that if you do this, it'll run, maybe about as well as maybe comparable to logistic regression. But it turns out that as we develop this algorithm further, there'll be a clever way to allow us to change this algorithm to let it work in infinite dimensional feature spaces and come up with very efficient nonlinear classifiers. So there's a ways to go before we can turn this into a support vector machine. But this is the first step. So the questions about this?
Do we need any assumptions about the position of samples in the space? For example, would you consider the points in the unit circle? Because if not, we can expand the space and the margins improve the quality of the signatory.
So for now, let's just say you're given a fixed training set and you can't, for now, let's just say you're given a fixed training set and that the scaling of the training set is not something you get to play with, right? So everything I've said is for a fixed training set, so that you can't, so that you can't change the x's and you can't change the y's. Are there other questions? Right. Okay, so what's one thing else? Okay, so all right, next week we will take this and we'll talk about optimization algorithms and work our way towards turning this into one of the most effective off-the-shelf learning algorithms. And just final reminder again, this next discussion section will be on MATLAB and Octave. So show up for that if you want to see a tutorial. Okay, see you guys in the next class.